All right, everybody, why don't we go ahead and get started? Good afternoon. It's my pleasure today to introduce Professor Brad Foley from Penn State University, an expert on geophysics and geochemistry and plate tectonics. Brad began his career at USC, and then he went on to get his PhD at Yale University with Dave Bercovici, sorry. Sorry about that, Dave. And from there, he went to DTM at the Carnegie Institute for Science in Washington, D.C., working part of that time with a former UW postdoc, Peter Driscoll, who's now a staff scientist there. And now he's in his third year as an assistant professor at Penn State University. And so today he's going to tell us about this possibility of habitability of stagnant lid planets. And so with that, I'm going to just turn it over to Brad. So thank you. And let me unmute you, excuse me.
All right, can everyone hear me? Yeah, sounds good, right? Mike's good. Okay, yeah, so thanks for inviting me out here. Thanks for your introduction, Rory. And like Rory said, like my title says, this talk's going to be all about the prospects for habitability on stagnant lid planets, right? And by habitability, what I'm really going to focus on is climate. What kind of conditions would allow a planet in a stagnant lid regime to maintain a temperate climate over geologic timescales, so life could potentially evolve on a planet like that, right? So we're thinking about stagnant lid planets instead of plate tectonic planets, right? So this is an example of stagnant lid convection here, shown from some numerical convection models I've run, all right? And the basic idea here is in a stagnant lid regime, right, the lithosphere, the surface of the planet, right, has a very high viscosity, right? It's really rigid, right? So the surface of the planet, it's rigid, it's immobile, and convection just takes place kind of spinning around beneath this not moving lid, right? So there's no subduction, we're not subducting crust and surface rocks and bringing them straight down to the interior of the planet. All right, so this is going to really change things about how, carbon white cycle and how a planet like this might maintain habitability. Right. All right. So as an outline, I'll just start off by giving you some motivation for considering stagnant lid planets and their potential for habitability. All right. And then there's going to be two main parts. All right. So the first part, which I'll probably spend most of the talk on, all right, is going to be looking at just kind of quantifying outgassing rates of CO2 on stagnant lid planets and seeing how long can sufficient CO2 outgassing, right, or enough CO2 outgassing to the atmosphere to keep the climate from freezing over and going to a snowball state, how long could that last on a stagnant lid planet? And what are the conditions that control that, right? And then the flip side of this, we'll be thinking about the opposite end member, making sure these planets don't get too hot, right, which is looking at whether stagnant lid planets can avoid this thing called supply-limited weathering, which I'll define later in the talk, right, where basically your outgassing of CO2 outstrips, outpaces what weathering can do to bring CO2 out of the atmosphere, and the climate would get really hot. Right, so we'll look at those two end members and what conditions lead to a kind of sweet spot, Goldilocks zone between those two problems. Right. All right, so then part two of the talk, right, instead of just looking at outgassing rates, I'll actually try to bring the climate into this, right, and really model how climate evolves. We'll look at things like initial conditions. Does it matter whether a planet starts with an initially warm atmosphere, lots of CO2 in the atmosphere, or if the planet starts cold and has to outgas CO2, right? And one of the main things I'll look at in this part two, right, which is an important thing, is whether a stagnant lid planet could potentially recover from a snowball type scenario. So, if something that we're not considering, maybe kicked one of these planets into a snowball state, is there enough, outgassing, enough CO2 to get the planet out of this state and back into a temperate, habitable climate, right? All right, so a great starting point for this, which you're probably all very familiar with for this audience, is looking at the habitable zone, right? So this is a figure from one of our recent graduates at Penn State, Sonny Harmon, right? Worked with Jim Casting, right? Just showing, the habitable zone based on some different estimates for different types of stars, right? And the main reason I show this, right, and the kind of point I want to make about the importance of thinking about the interiors of planets and their outgassing history is that in order to make this figure of the habitable zone, even the conservative habitable zone is actually still pretty optimistic, right? So even this conservative habitable zone, right, is actually thinking that, a planet near the inner edge, right, has kind of just the right atmospheric makeup to not make it too hot, right? Or planets near the outer edge have just the right amount of greenhouse gas warming to keep them warm, right? So this is kind of the best case scenario, right? Kind of assuming that planets have some ability to regulate their climate, right? So that even within this habitable zone, I can put the giant stick away. Right, so let's see, what was I saying? Oh yeah, so that the idea of the habitable zone is sort of optimistic in that we're assuming that planets can regulate their climate in a way so that even with these variations in solar luminosity, right, you still have temperate climates, right, based on where you are. Right? So like I just said, we need some type of climate regulation, right, in order to have planets across this habitable zone actually be habitable over geologic timescales, right? So of course the solar luminosity varies both in time and in space, depending on where in the habitable zone you are, right? And also CO2 outgassing rates vary as well. You know, you could have a kind of random fluctuation that leads to a bunch of CO2 being outgassed into the atmosphere. That could cause a big climate perturbation if we don't have some regulation of atmospheric CO2, right? And the big thing we talk about, right, is the carbon cycle, or the carbonate silicate cycle, right, that has these negative feedbacks that help stabilize climate by regulating the atmospheric CO2, right? So if you have a planet, let's say, has a constant amount of CO2 in the atmosphere, that's this dashed line, right? And you look at how its climate would evolve as solar luminosity evolves, right? This planet would warm up really quickly, right? And have only spend a short amount of time in this sort of nice temperate climate zone. But if you have the carbonate silicate cycle active, right, and regulating atmospheric CO2 levels, right, then when you've got, say, a lower luminosity, right, you can have higher amounts of atmospheric CO2, bring the temperature up, right, and as you get to higher luminosities, the atmospheric CO2 goes down, right, keeping your temperature, you know, not as hot as it would be, right, without this buffering effect, right. So this is an important thing in order to make planets in the habitable zone actually be habitable in practice, all right. So the carbonate cycle, the silicate carbonate cycle, on Earth at least, seems to be intimately tied to plate tectonics, right? So the tectonics of the planet seems to matter, right? So on Earth, plate tectonics is largely responsible for most of our volcanism, right? So volcanism at mid-ocean ridges, it's a plate tectonic process. Volcanism at island arcs above subduction zones, right? Another plate tectonic process, right? So this is our main CO2 input to the atmosphere, right? At the same time, plate tectonics is recycling CO2 from the surface back into the interior, right, into the mantle. So it's kind of replenishing our supply of CO2 in the mantle so that outgassing doesn't just die out over time, right? And the other thing that plate tectonics helps do on Earth, right, is it replenishes our supply of fresh weatherable rock at the surface, both through mountain building processes like colliding two continents together and building something like the Himalayas or the Tibetan Plateau, and also just through volcanism, both on land and also at the seafloor, you know, creating fresh rocks on the seafloor that can undergo seafloor weathering as well, right? So we've got these two important things, you know, the outgassing of CO2 to the atmosphere and the removal of CO2 by weathering. Both of them are kind of, at least in some ways, tied to plate tectonics, right? So just to drive this point home further, so this is a figure from some work by Kadoya and Tajika, right? And they looked at varying the CO2 outgassing rate, right? So these are CO2 outgassing rates normalized to present-day Earth, right? So 1 would be present-day Earth here, right? And they looked at this in terms of incoming solar flux, right? Also normalized to the solar constant for today here at 1, right? And what they found is, you know, there's a kind of critical threshold, right, of outgassing rate, right, that you need in order to avoid a snowball climate. Basically, you have to be putting enough CO2 in the atmosphere, right? Otherwise, weathering pulls all this CO2 out, and you end up in a frozen snowball state, right? Or, you know, in reality, it could be this limit cycling behavior where you have a snowball state that lasts for a while, outgassing warms the climate up, melts really quickly, and then gets plunged back into the snowball state. Right? But the main point is, you know, there's some kind of critical threshold, some limit, right, of outgassing that we need in order to keep a planet's climate from being too cold. Right? Right? And the opposite side of that, right, we need some, you know, climate regulation in order to keep the climate from being too warm, right? And this gets at this idea of the supply of weatherable rock at the surface, right? So there's this idea where if you don't have enough kind of fresh rock being thrust up to the surface that can undergo weathering, you reach this limit that's called the supply-limited weathering regime, right? And when weathering's supply-limited, it no longer depends on climate, right? So there's no weathering climate feedback, right? Because what's happening is all of the fresh rock that's getting exhumed or exposed at the surface, either through mountain building or through volcanism, creating fresh lavas, all of it gets weathered completely, basically immediately, right? So all that matters is the rate at which this fresh rock is being brought to the surface, right? So if that happens, you can't balance the outgassing rate with the weathering rate anymore, and CO2 just builds up in the atmosphere. Right, so this is an example from an earlier paper of mine looking at decreasing the amount of exposed land, so thinking about weathering on continents, on land, right? So as you decrease the amount of exposed land, right, that's going to the left in this diagram, you eventually reach the point where you hit the supply limit to weathering, right? The weathering rate can't go up anymore to balance the outgassing rate. So instead, we just accumulate a ton of CO2 in the atmosphere, right, and end up with a really hot climate. Right? So both of these things are important in order to get a planet to have a climate that's in this temperate, moderate state. Right? Okay, so we need this climate regulation. It seems to be, at least in some ways, tied to plate tectonics. Right? What do we expect to see for plate tectonics on exoplanets? Right? And this is something I've worked on in the past, many other geodynamicists have worked on. And I think the punchline for non-geodynamic specialists is basically, we don't know. Right? This is unclear. Right? Plate tectonics is a really complicated process, and we struggle to understand it, and we struggle even more when we try to predict what will happen on exoplanets. Right? So these are two studies that came out more than 10 years ago now, from Diana Valencia and then Craig O'Neill and Adrian Lenardic, right? And they reached opposite conclusions about whether increasing a planet's size will make it more or less likely to have plate tectonics. Diana kind of argued that as you increase a planet's size, the stresses from mantle convection will go up, right? And that the strength of the plate would go down, so then you'd expect it to be easier to break up the surface rocks and make plates, right? But then Craig O'Neill pointed out, right, that actually as you increase planet size, if you also crank up the internal heating rate in the planet gets much hotter in the interior. That actually drops the stresses from mantle convection that are being applied to the lithosphere. And that might push you into a stagnant lid regime on larger planets instead of a plate tectonic regime. All right, so I bring these kind of opposing views up to make the main point that plate tectonics is really complicated, and we don't understand it that well. And we definitely don't understand how it works on Earth very well. It's even harder to predict what we see on exoplanets. And there are a lot of things that could be important, things like not just planet size, but heat budget, mineralogy of the planet, surface temperature, all sorts of things could be important. So it's going to be really hard to predict whether planets have plate tectonics or not. Right? I do want to point out, so this is some of my own work on this issue of super Earth plate tectonics and what we'd expect to see. It is possible, right, based on the work I did, that planets in the habitable zone, right, might actually be more likely to have plate tectonics, which would be kind of a good thing, right? And some of the reasoning for this, the work I did, we were looking at trying to make plate tectonics by causing significant reduction of grains, mineral grains in the rock, right, which makes the rock weaker, right? And it turns out that to do this, it's really helpful to have cool temperatures in the surface of the planet. Because when the temperatures are cooler, right, you can drive the grains down to smaller size. When the temperatures are warmer, the grains want to grow back really quickly, and you can't drive them down to a smaller size. Right? So it might actually be beneficial to have a cool surface temperature, right, like shown on this diagram, where there's a bigger plate tectonic range as the surface temperature is lower. Right? And there's other work from other geodynamicists, some from June Kornaga, Adrian Lenardic as well, about the importance of water. Right? That would be another link between the surface environment and plate tectonics, and maybe make it easier to have plate tectonics for planets in the habitable zone. But in the end, I'd really say that we don't know, right? And it's going to be really hard to predict whether planets in the that we find are going to be plate tectonic planets or stagnant lid planets, right? And just to belabor this even more, if we just look at our solar system, right? Our solar system would kind of indicate that plate tectonics is probably the weird scenario, the less likely scenario, right? So Earth has plate tectonics. Our neighbors in the solar system definitely don't have plate tectonics, right? Oh, and the previous one, that was just for convenience, actually. You can't exactly constrain where the boundary is, so we intentionally fixed it to Earth just to see what the trend would be with planet size and surface temperature.
So what determined the slope of that line?
So that's coming from the physics of this effect of surface temperature on grain size reduction in the rocks and how much weakening you can do to make plate boundaries. Right? That's a whole nother talk, which I'm kind of just using for motivation here. All right, so it's going to be really hard to tell whether we've got, or predict whether we're going to have stagnant lid planets or plate tectonic planets. All right, so my pitch here is that we should think about stagnant lid planets. and whether they might be habitable as well, and whether these same processes that are important for regulating climate, right, can take place on stagnant lid planets. All right, so even just looking at Mars here, right? So Mars has significant volcanism. There's this Tharsis Rise province with big volcanoes like Olympus Mons. All right, so stagnant lid planets still have volcanism. All right, that both creates fresh rock at the surface for weathering. That's good, and it can outgas CO2 from the mantle. Right, so both of these processes that are kind of tied to plate tectonics on Earth, are at least possible on a stagnant lid planet. Right. So the big question then, right, that we're going to explore is, can CO2 then be cycled, right, back into the mantle, or maybe released from the crust to keep outgassing rates high? Right? If we can't do this recycling, well, what you'd imagine would happen is maybe the mantle starts with some CO2, it gets outgassed to the surface, right, but the outgassing rate will drop away really quickly if there's no way to kind of resupply CO2 into the mantle or maybe release it from the crust. Right? And then the other question is there going to be enough weatherable rock being created, right, from volcanism in order to prevent this supply-limited weathering, right, from making the climate too hot? All right, so I'm going to model stagnant lid convection, right, in this kind of framework. So we've got a rigid lithosphere, that's our stagnant lid. Right, there's convection happening beneath this lid, right? And based on the temperature profile through the lid and the temperature in the mantle and the melting temperature of rocks here, and this is all going to be kind of thinking about Earth-like planets, Earth-like compositions. That's where we know all these properties the best. Right? There'll be a melting region beneath the lithosphere, right, where some partial melting happens, and this can create volcanism at the surface. Right? Right, so on a stagnant lid planet, right, this melting and volcanism will lead to formation of a crust. Right? It has a different composition from the rest of the mantle. It's going to be presumably basaltic, like the ocean crust on Earth. Right? But because we don't have subduction, taking this surface material back into the mantle, the crust is actually just going to grow in thickness over time. Right? You erupt some lava, you make some basalt. Right? You erupt more lava, you bury the stuff that was before it, and you keep this process going. Right? So the crust just gets thicker and thicker over time and grows kind of deeper down into the lithosphere. All right. And again, assuming that we have this Earth-like composition, right, as basalt gets buried to higher and higher pressures, gets buried deeper in the lithosphere, right, and that can undergo a phase transformation to a dense form called eclogite, right, a denser rock, right? So this stuff is dense, right, and then that means that crust might want to founder, right, from the base of the lithosphere back down into the mantle, right? So as this crust grows, right, and gets towards the base of the lithosphere, right, it can transform into eclogite. Temperatures are also warmer here, so the rock viscosity isn't super high, so stuff can potentially founder, right, and delaminate down into the mantle, right? So that's a potential mechanism for actually recycling CO2 from the surface back into the mantle, right? All right, but there's another process that's important, right? And that's that before the crust makes it all the way down into the deeper lithosphere where it can delaminate into the mantle, it actually might undergo metamorphic reactions that release the CO2 in the crust, right? And this is what turns out ends up being the more important mechanism, right? So to do this, I teamed up with a colleague at Penn State, Andy Smye, who's a metamorphic petrologist, right? And he helped calculate the phase assemblage of minerals in a carbonated basalt, right? And their stability in temperature and pressure space, right? And that's this very complicated diagram here that metamorphic petrologists love, and the rest of us are, if you're like me, you're terrified by. But we can look at this much simpler one on the right, which is showing the CO2 weight percent, right? So here in our red colors, lower temperatures, right? We've got lots of CO2 in the basalt. It's stable and happy there. As you go to high temperatures, right, you lose this CO2 very quickly, right? So metamorphic decarbonation reactions kind of kick the CO2 out of the crust and push it up to the mantle, right? So as crust is getting buried, it's going to get to high enough temperatures where these reactions kick in, right, and we get outgassing from the crust, right? So you've got a kind of flowchart diagram of what's happening here, right? So you've got CO2 in the mantle, right? Mantle volcanism is releasing this to the surface, right? Then we just assume that weathering is going to deposit this in the crust, right? The carbonated crust gets buried by later volcanism, so this crust gets kind of pushed down over time, right? And then it's going to hit a level where the temperature conditions are such that these decarbonation reactions kick in, right? And we get outgassing of CO2, right, from these metamorphic reactions back up to the surface, where again it gets weathered out and put back in the crust, right? and then this foundering of crustal carbon back into the mantle, we found that actually that ended up not really occurring. You basically always just had these metamorphic reactions kick in, right, and take the CO2 from the crust back to the atmosphere. Right? So actually what happens is we lose CO2 from the mantle to the crust over time, and then it just cycles through the crust, right, as long as volcanism is active. All right, a couple of limits we're going to look at. So we want to see what is the outgassing rate, and is it combining both volcanism and this metamorphic decarbonation of the crust, right? And is this outgassing rate enough, right, to keep the planet's climate from going into a snowball state? Right, so I used this work from Kadoya and Tajika to give me some kind of basic M members here, right? And they found, it depends on the solar flux that the planet's receiving, but something like 100% to about 10% of Earth's present-day degassing flux, right, would be enough to keep the climate warm, right? So we can constrain that, right? We can see our outgassing rates meeting this threshold, right? And then we can also see whether weathering can keep up with outgassing of this supply-limited weathering I talked about. Right, so we do a thermal evolution model. Right, it's going to track the cooling of the mantle, the evolution of outgassing and volcanism, right? And here's a big laundry list of assumptions, which is maybe more detail than we need for right now. But just to go through some of the key points, we're going to assume the mantle is purely internally heated, right? So purely heated by either, by radiogenic heating, right, and heat it from formation. We're going to track partitioning of heat-producing elements into the crust. So as we make the crust, some of these heat-producing elements actually prefer to go into the crust rather than stay into the mantle. And that's important, right? Because if we didn't do that, we'd kind of overpredict the heating power in the mantle, right? Only a fraction, about 10% of the melt that's produced is going to erupt at the surface, right? And that's what we use to calculate this supply-limited weathering rate, right? We also track that the amount of cooling that comes from volcanism, right? So actually just melting the mantle and erupting this lava at the surface helps cool the mantle pretty significantly. All right, we'll assume that all of the melt that's formed degasses completely, and we're going to assume that the crust delaminates, right, gets foundered back into the mantle, right, when it reaches the base of the lithosphere, what I call the thermal lithosphere, which is controlled by the mantle convection, right? So mantle convection kind of sets how thick the lithosphere should be. All right, so those are some of the key assumptions. All the details here are in our astrobiology paper that came out this summer. It's way too much to go through in this talk. All right, so here's an example of what the model results look like, right? And this is also kind of overly busy, but I'll draw you here to panel B, right, and panel C, right? And these are showing the evolution of the CO2 outgassing rates and the amount of carbon or CO2 in the mantle and the crust reservoirs, right? So if you look at panel C here, so here's time, right, going from 0 when the planet first forms and starts its thermal evolution up to 6 billion years, right? And here's the amount of CO2 in the mantle is a solid line, right? And in the crust is this dashed line, right? So we start off with all the planet's CO2 in the mantle, right? There's nothing in the crust because the crust doesn't exist yet until volcanism kicks in, right? And what happens is we very rapidly lose CO2 from the mantle, accumulate it in the crust, right? And then we put most of the planet's CO2 actually in the crust, and the mantle gets very depleted, right? Because there's actually no mechanism for recycling CO2 back into the mantle because this metamorphic decarbonation kicks in, right, before you can founder this stuff into the mantle, right? So then if we look at the outgassing rates, right, so the dashed line here, that's outgassing from the mantle, from mantle volcanism, right? The dot dashed line here, which is kind of hard to see, is the metamorphic outgassing rate, and then this kind of blue line behind them is the total of adding the two together, right? And it turns out that the mantle volcanic outgassing rate drops away really quickly, right? And the planet actually gets dominated by metamorphic outgassing, right? Outgassing coming from decarbonating this crust, right? So it's actually the decarbonation that ends up being the much more important thing, right, for sustaining outgassing on a stagnant lid planet, right? So this one's really the key for keeping the climate warm. All right, let's talk about the supply-limited weathering flux, right? So how do we formulate this, right? So the idea of the supply limit to weathering, right, is it's the rate at which CO2 would be drawn down by completely weathering all of the rock as soon as it's kind of exposed to the surface and available to be weathered. Right? So what I'll assume for these stagnant lid planets is that since we don't have big mountain building collisions like you get in plate tectonics, right, I'll assume that all the fresh rock we have available to weather is rock that's being erupted by volcanism. right? So the supply limited weathering flux is then given by the flux of erupted lava, right, which is these two terms, right? And then we have some parameters, right, that basically take this flux of erupted lava and tell us how much CO2 can you draw out of the atmosphere based on reacting all of the reactable elements within this basaltic lava with CO2 in the atmosphere. All right, so we get a formulation that looks like this. And the key point is, these things are material properties. It's basically just based on the composition of the rock, right? And this guy is the rate at which we're creating magma in the mantle and erupting it at the surface. All right. All right, so we'll be in this state where outgassing is overwhelming weathering and leading to a really hot climate when our outgassing rate is larger than this supply limit to weathering, right? Then the weathering gets stuck at the supply limit. If your outgassing rate's larger, you just accumulate CO2 in the atmosphere and the climate gets really hot, right? So you can think about the kind of critical state where outgassing first equals the supply limit to weathering, right? And write it like this. So here's the mantle outgassing rate, right? The outgassing rate from metamorphic decarbonation of the crust, right? And we'll set this equal to the supply limit to weathering. All right, so the mantle outgassing rate, right, it's just dependent on the amount of CO2 in the mantle. That's our man, right? This is basically the volume of the mantle itself, right? This phi here is the melt fraction, right? And FM is the rate at which melt is being produced, right? The volume rate, right? The metamorphic outgassing rate is very similar, right? It also depends on the rate at which melt is produced, right? The amount of CO2 in the crust, right? And the volume of the crust. Right? And then we've got our supply limited weathering rate, which we talked about earlier. All right, so a key point, all of these have this variable FM, right, which is the rate at which melt is being produced. Right? So you can cancel those guys out, right? And we can see that whether we reach or hit this supply limit to weathering and would end up forming a really hot climate on a planet is mainly just dependent on the amount of CO2 we have in the mantle and the amount of CO2 we have in the crust, right? So these volume terms, they don't really, the volume of the crust changes some as the crust grows, right? But the big factors are how much CO2 we have in the mantle and how much CO2 we have in the crust, right? So if we have more than some kind of critical threshold, right, then every time we're erupting lava and burying the crust and decarbonating this crust, right, we'll be putting more CO2 in the atmosphere, right, then weathering could possibly take CO2 down, right, based on weathering all of this fresh rock that's been erupted, right? So whether we hit this uninhabitable climate state is mainly just a function of the amount of CO2 in the system, right? So that leads us to these kind of summary figures, right? So what I did is I ran a whole bunch of models, right, like the one I showed where I was just showing one particular model and its time evolution, right? And I varied the total amount of CO2 in the system, right? So that would be adding both the mantle and crust reservoirs together, right? It gives us this total amount that's conserved for a planet, right? And I varied the amount of radiogenic heating that the planet starts off with, right? So the radiogenic heating rate, right? So the radiogenic heating rate, you start with some initial amount, and it decays following a decay law over time, right? So this is just looking at the amount we start off with in the planet, right? So we've got that, this, right? And then I calculated how long do each of these models give us an outgassing rate, combining both volcanic and metamorphic outgassing, right? That's either higher than the present day, so that's a figure on the left here, right, or higher than 1/10 of the present day Earth's outgassing rate, right? That's a figure on the right here, right? And these are color-coded based on time in billions of years, right? So we've got here 0 billion years, right, that we have outgassing rates high enough, right, here 1, 2, 3, 4, right? And then the shaded region, right, to the right of this dashed line, that's where we hit the supply-limited weathering regime, right? So that's where outgassing would outpace what weathering could do, and you get a really hot climate, right? So summary, these purples, right, that's where the planet wouldn't be habitable because it's too cold, right? And the shaded region here wouldn't be habitable because it's too hot, right? Way too much CO2 in the atmosphere. And this kind of colored regime in between, right, that's where habitability could potentially last for 1 billion years, 2 billion years, and on up, right? So it depends strongly on the total amount of CO2 in the system, right, and this initial radiogenic heating rate, so basically the heat budget available to drive the planet's thermal evolution, right? So the dependence on the radiogenic heating rate is pretty easy to understand. Basically, the higher the radiogenic heating rate you start off with, right, the more power you have to drive convection over time, right? So the planet stays hotter, volcanism stays active, right? So as long as volcanism is active, we can have some outgassing of CO2, right? So the higher the radiogenic heating rate, right, the longer volcanism lasts. Right, so then we have this dependence on the total amount of CO2 in the system, right? And you can see that when it's too low, right, we end up with a really cold climate, right? When it's too high, we hit the supply-limited weathering regime, right? And I think that basically, is fairly intuitive to understand. So in this region here, where we've got too little CO2, there's still volcanism happening, right? But the amount of CO2 that's coming out as a result of this volcanism and the metamorphic decarbonation of the crust just isn't sufficient to keep the climate warm, because there's basically just not enough CO2 in the whole system, right, to give us the outgassing rates we need to keep the climate warm, right? So as you go to low CO2 budgets in the whole planet, right, you end up with climates that are too cold, right? And the opposite happens when the CO2 budgets are too high, right? This is like what I was showing in the previous slides, right? You reach a point where there's just too much CO2 in the system, right, for weathering to be able to handle the outgassing rates you'd get. So you'd end up with a planet that's too hot. All right, but we have this sweet spot in between, right, where habitability is possible. And to give you some idea of where the Earth would lie, so we think the Earth has a CO2 budget of something like 10 to the 22 moles, right, an initial radiogenic heating rate of something like 70 to 100 terawatts. So we maybe plot kind of in here, right? So a planet with a CO2 budget similar to Earth, right, would be good, maybe down to 1 or 2 orders of magnitude lower than that, right? And if you can crank up the internal heating rate, if a planet acquires more uranium and potassium and thorium when it forms, that would allow it to have a longer-lived, habitable climate than an Earth-like planet would, right? All right, so I did a bunch of sensitivity tests with this. I probably don't need to go into all of it, but I changed some important things, like up here I changed what I call the reference viscosity, which is like the background viscosity of the mantle, right? And I changed the initial temperature of the mantle, right? That's these guys, all right? And some of the main results that you find in this, which are kind of interesting and potentially be important for thinking about, planets and whether we'd, expect them to be habitable or not, and for how long, is that the lower the viscosity is, right, then the shorter our habitable lifetimes are, right? You see we've got a smaller space of these, few billion year lifetimes of outgassing here. When the viscosity of the planet, the kind of bulk average viscosity of the mantle is lower, right? When the viscosity is higher, you get the opposite effect, right? And habitable climates can potentially last longer, right? And the reason for that is pretty simple. So if viscosity is lower, right, that planet will convect more vigorously, its heat flux will be higher, it'll cool off quicker, right? So the lower viscosity, the more our planet will cool off quickly, right? Its mantle will quickly get so cold where volcanism dies out soon, right? Well, on the opposite end of that, if a planet has a higher viscosity, right, its convection is less vigorous, its heat flux is lower, so it stays hot longer, right? And so outgassing can last longer because there's still melt being produced in the planet for longer, right? Changing the starting temperature didn't have too much of an effect, right? The only thing that's kind of important here is that when the initial temperature is low enough that melting doesn't begin right away, we get a little range here where we would have had habitable climates lasting for, a billion years or so when we start off with a warmer temperature, but here we don't because, we need more radiogenic heating for the planet to warm up enough to start melting, right? And then this slide isn't too important. I'll just show that you can change a whole bunch of model parameters, right? There's all sorts of things for the viscosity law, the melt production rate. We also looked at a case where there was actually no decarbonation of the crust, and actually all this carbonated crust did get recycled back into the mantle. Other various things. Basically, you get very similar results, right? So the models are, the details could be a little different depending on how you change parameters, but the kind of take-home message that we've got this kind of decent-sized sweet spot where long-lived habitable climates are possible on a stagnant lid planet. That stays the same, right, as we change model parameters. All right, so this is part one, so I'll just wrap up with some implications and summary of part one, and then we'll go into part two. Right, so what we found is stagnant lid planets can potentially sustain habitable climates, right, for something like up to 4 to 5 billion years if there's lots of heat-producing elements in that planet, right? Showed you that the metamorphic outgassing of buried carbonated crust is actually the main mechanism for driving this long-lived outgassing. So it's really more about this crustal burial rather than actually volcanism release of CO2 from the mantle. Right? And to put some numbers on this, planets with CO2 budgets of something like 1/100th to 1 times Earth's CO2 budget, right? And initial radiogenic heating rates, right, of similar to Earth's or higher, is the kind of sweet spot for long-lived habitable climates on stagnant-lid planets, right? So you said if you have less CO2 than this, the outgassing rate's too small and the planet's cold. If you got more CO2 than this limit, right, then the planet gets too hot, right? And lastly, if you know the planet age and can try to constrain the heat budget based on the stellar composition, we can maybe place some constraints on whether a particular planet we find could actually be outgassing, right, and habitable, even if it's in a stagnant lid regime. So there's some potential power here for target selection and then maybe testing this with observations. All right, so going to part 2 now. So part 2 is, before here, in this first part, we were just looking at the evolution of outgassing rates, right? Constraining this from the thermal evolution of the planet. All right, but now I want to look at how climate actually evolves on these planets, right? And I want to look at whether the initial climate conditions matter, if the planet starts off cold or hot, right? And then maybe most importantly, or most interesting to me, whether a stagnant lid planet could recover from some kind of snowball state like this, or whether maybe it would be stuck in this snowball state if one were to occur, right? All right, so what I'm going to do is I'm going to first assume that actually these planets are going to be dominated by seafloor weathering, right, rather than continental weathering. And the idea behind this is that stagnant lid planets, I'd argue probably lack felsic crust in continents the way we have on Earth, because the continents seem to be largely made by plate tectonics on Earth, right? So a stagnant lid planet is going to mainly just be creating basaltic crust, right? So it might be hard to create the kind of topography dichotomy like we have on Earth that gives us oceans and land. So I'm just going to assume that we've got predominantly seafloor weathering, right? I'm going to use the weathering rate formulation and parameters from Josh and David's papers, right? And with a couple of modifications. So the weathering rate's going to be dependent on temperature, right? Like in Josh and David's work, right? But instead of making it dependent on the seafloor spreading rate, which we don't have on a stagnant lid planet, I'm going to make it depend on the eruption rate, right, of lava at the surface, right? Because basically the spreading rate dependence is getting at the amount of fresh rock that you're creating from the plates diverging apart and creating new crust, right? And so what I've done is I've taken this kind of standard seafloor weathering rate and I've wrapped it in this really complicated, weird-looking equation which gives the supply limit to weathering, right? So basically what happens is when the weathering rate is below our supply limit to weathering, it follows this normal temperature-dependent weathering rate, and then this complicated exponential stuff just causes it to smoothly flatten out at the supply limit to weathering when we reach that, right? All right, so we've got that weathering rate. I'm going to parameterize temperature in the same way that Josh and David did as well, right? So we've got a surface temperature that depends on CO2, right, in this simple formulation. Right, the ocean bottom temperature is going to depend on the surface temperature, right? And then I use a formulation from a paper by Mills et al. In 2011 to capture the partitioning of CO2 between the ocean and the atmosphere, right? So this formulation gives us the fraction of CO2 that's in the combined ocean-atmosphere reservoir that's going to be in the atmosphere rather than the oceans, right? All right, and here's an example result. So here's a, similar to what I showed before with this time evolution modeling result. So there's one individual model with a particular total CO2 budget, a particular heat-producing or amount of heat-producing elements at the start of the model run, right, that decays over time, right? And I'm showing the evolution of surface temperature, right, and the evolution of CO2 in the atmosphere. And since I want to think about initial conditions, right, there's two basic n-member cases I tried, right? They called a hot start, right, and a cold start. Right, so in the hot start, I assume that almost all of the CO2, basically 99.9% of the CO2, initially resides in the atmosphere and ocean. Right, so the climate starts off really warm. All right, in this cold start, I assume that the climate starts off just above the freezing point for water, right? And then we see how the system evolves from there. I don't want to go colder than that because with the climate parameterization I'm using, we can't really capture what happens in a snowball scenario, right? The main punchline here is that both of these initial conditions actually lead to very similar climate evolutions, right? So the cold start here is shown in the solid line, right? So it starts off with a low CO2 value, right, and a low surface temperature, which very quickly shoots up, right? You can hardly even see it. It's just almost tied to the y-axis here, right? And then it becomes very similar to the hot start scenario, and then they evolve similar over time, right? So whether you start cold or you start hot, right, these things tend to merge the same kind of evolutionary track very quickly, right? So it turns out these initial conditions don't seem to be particularly important, right? And that's the same result we get when we look at now a summary plot similar to what I showed earlier, where in this case I'm saying how long do habitable climates last, since I'm tracking the surface temperature, right, in the same space of the total CO2 budget of the planet, right, and the initial radiogenic heating rate of the planet on the y-axis, right? And this is now colored out to 0 to 6 billion years for how long habitable climates are lasting, right? So this is showing the hot start scenario, right, and the cold start scenario, right? And the kind of main punchline here is these things look pretty much the same, right? So it doesn't really matter in terms of how long a habitable climate lasts, whether you start off with a really hot climate or a colder climate, right, and need outgassing to warm things up. All right, a couple other important things that you can see with this. So if you can remember the slides I showed earlier, right, where I was just looking at outgassing rates and not actually modeling the climate evolution and thinking about seafloor weathering, right, this span of CO2 budgets, right, where we're getting habitable climates to develop and last for a while, it's actually wider than it was before, right? So actually things get better, right, when I do this more kind of sophisticated model of thinking about climate evolution and seafloor weathering, right? And there are two main reasons for that. One is, so this dashed line is showing where supply-limited weathering starts, right? So to the right of that is this supply-limited weathering regime. And it turns out, the uninhabitably hot climates don't develop immediately when you cross over into the supply-limited regime. You have to kind of push into it a little ways before things get really hot, right? So there's some planets, out here within this nominally supply-limited weathering regime that might actually be habitable for a few billion years, right? We also end up predicting that planets at lower total CO2 budgets than we saw before could also be habitable, so kind of this range, right? And that's because the seafloor weathering is actually a little slower than continental weathering, right? So when you have mostly seafloor weathering, you end up with more CO2 in the atmosphere for a given outgassing rate than if you had continental weathering dominating, right? So things actually end up looking a little better in this case. All right. Again, we tried different scenarios, different initial mantle temperatures, different viscosities. The main punchline with this diagram is to show you that these different initial conditions look the same, right? Okay, so in the last few minutes here, we'll talk about recovering from a snowball climate, right? So, I thought this was an important thing to think about because even though we've got outgassing rates that we think should keep the climate warm, something kind of unexpected could happen. Some other perturbation we're not capturing could maybe kick a planet into a snowball state, and we want to know, can it actually get out of this snowball state and go back to having a temperate climate, right? So I'm going to consider two n-member cases, right? What I'll call a hard snowball, right, and a soft snowball. All right, so the hard snowball, I'm going to say that there's no exchange between the atmosphere and the ocean, right? So we must outgas CO2 directly into the atmosphere in order to warm the climate up, right, and get out of this hard snowball state, right? And the big assumption I'm going to make with this scenario is say that only mantle volcanism, right, releasing CO2 from the mantle, right, is actually going to be outgassed directly to the atmosphere. So I'm thinking of volcanism coming out of big volcanoes that might be sticking up above the ice layer. Our metamorphic decarbonation, that's going to be occurring in kind of low-lying plain regions. That might be, or I'm going to assume that would be beneath an ice layer, right, in a hard snowball state, right, where we're assuming that nothing that's coming into the ocean beneath the ice layer can get up to the atmosphere. We're going to say that we can't rely on this metamorphic decarbonation, right, to warm the climate out of a hard snowball. All right, in a soft snowball state, it's the opposite of that. We will assume that there is exchange between the atmosphere and the ocean, right? So both our metamorphic outgassing and our volcanic outgassing can contribute to warming the climate out of this snowball state, right? And we'll also assume that, in this case, seafloor weathering will actually still be active, right? Because it would be drawing CO2 out of the oceans, which is then, by exchange with the atmosphere, effectively drawing CO2 out of the atmosphere as well, right? All right, so basically what I'm going to do is I'm going to take our model results. I'm just going to integrate these outgassing fluxes for these different snowball scenarios, right, and see can we get out of a snowball that starts at a particular time, right? And I'll imagine that at each time during the evolution of our planets, right, that I'm modeling, I'll say, let's say, what if a snowball starts at this time? Can we get out of it? Go to the next time. What if a snowball starts at this time? Can we get out of it? Right, and we'll track the latest time in the planet's history, right, when it can recover from a snowball state, either the hard snowball or the soft snowball. All right, so here are the results. All right, plotted on these same axes I've been using of total CO2 budget, right, and the initial radiogenic heating rate, right? And now we've got hard snowball scenarios here, right, for both a hot start initial condition and a cold start initial condition, right? And then soft snowball scenarios down here for the same initial conditions, right? So we just look at the top plot first, right? You'll see we've got a hot start, and we're trying to recover from a hard snowball, right, where only mantle volcanism can warm the climate up and get you out of it, right? And we're calculating, right, how long into the planet's history can we recover from this? So the blues are basically 0, and anything not blue is getting up to 500 million years. All right, this plot, you just see blue, right, except at this very extreme end. All right, so the punchline here is that if you start with an initially hot climate, right, most of the plant CO2 initially sits in the atmosphere, not in the mantle. Right, so the mantle outgassing rate is pretty low, right, and it's low throughout the planet's history because you never get CO2 back in the mantle. It all just cycles through the crust. Right, so if a planet like that got stuck in one of these hard snowballs, right, where you need mantle outgassing, at least according to my assumptions, to get out of this snowball, right, it's basically impossible. Right, so if you start off with most of your CO2 in the atmosphere, right, and this planet got into a real hard snowball state, it'd be nearly impossible to get out of that state and recover. Right? If we start off with a colder start, right, where there's some CO2 in the atmosphere, but most of it's in the mantle, right, then the prospects are a little better. Right? So we've got time contours here showing how long in the planet's evolution you could get out of this hard snowball state for this scenario. Starting off here this is basically 0, right, this dashed line, and then going up to something like 2 billion years into the planet's history where you could recover. Right? So here, you start off with a lot of CO2 in the mantle, right? So the mantle outgassing rate is still high enough to bring you out of a hard snowball state, at least early in the planet's history. Right? But as the mantle gets depleted in CO2 over time and the CO2 goes to the crust, right, then you can't recover from this hard snowball anymore. Right? Okay, if we have a soft snowball, right, those are these results. Right? And in this case, it's much easier to recover from because both our metamorphic outgassing and our volcanic outgassing, right, can lead to warming the climate up. Right? So in this case, you basically can recover from a soft snowball, right, for either initial condition for about basically as long as volcanism lasts. Right? So for about as long as we would predict habitable climates to last anyway, right, you can get out of a soft snowball if it were developed. Yeah, in this case. Right? Let's see. All right. Another important thing here is the, right, so it's hard snowball and soft snowball. There are these limits, right, that I drew in these white dot dash lines here on the hard snowball case and the soft snowball case, right? And these limits are where, no matter what, right, the planet could never recover from a snowball, right, even if that snowball started basically as soon as the planet formed, right, so time 0. Right, and the idea here is if you're to the left, right, of this white dot dash line, there's not enough CO2 in the whole system that even when you put basically all that CO2 in the atmosphere, right, it's not enough warming to get out of the snowball state. Right, so we've got that limit. So this range here, right, a planet that started in a hard snowball would basically never be able to recover from it. Right? And we've got a similar limit for the soft snowball state, right, that's this white dot dash line. Right, and any planets that start off, that sit over here, right, with low CO2 budgets, right, would never be able to recover from a soft snowball if one were to develop. Right, and you'll notice that actually this limit is a little bit higher for the soft snowball state than it is for the hard snowball case. Right, and that's because you actually need to put more CO2 in the combined ocean-atmosphere reservoir to get out of a soft snowball state because we've got exchange between the two. Right, a hard snowball state, you just need to get this into the atmosphere. Right? All right, so if we take these limits, right, and kind of overlay this with our original kind of summary of where and how long habitable climates might last on a stagnant lid planet, right, we get some really interesting stuff. So here's our initially calculated baseline model results for how long a habitable climate will last, right, as a function of our same total CO2 budget, right, and initial radiogenic heating rate, right? And I've overlaid here these two limits where you could never recover from a snowball state, even if that snowball was at the very beginning of the planet's history. So if you started in this soft and hard snowball, right? So to the left of this dashed line, right, so this region that's shaded here, in this region of parameter space, a planet that starts off in a soft snowball, right, would actually never be able to recover from it, right? So planets existing, right, in this region, right, or especially kind of in this region, right, could have, if they start with a soft snowball, they'd be stuck in that state for their whole history. But if they started in a warm climate state, they'd actually be able to stay temperate and habitable for as long as these calculations show. So like say a planet here, right, could have a habitable climate lasting for 3 billion years if it starts off temperate. But if it started off in a soft snowball state, it would be stuck there, right? So there's hysteresis effects, right? And then to the left of this dot dashed line is the same thing, but for a hard snowball state. So a planet, say, sitting right here, right, would be able to have a habitable climate for something like 2 billion years if it starts off in a temperate state. But if it started off in a totally frozen hard snowball state, it would be stuck for its entire lifetime, right? So we've got hysteresis effects at low total CO2 budgets, right, based on the ability to recover from snowball states. Right? Okay, this is again showing that the results for how long habitable climates last are consistent for all these different model parameters. You see similar effects like the influence of the initial mantle temperature, the influence of viscosity. So higher viscosity planets, again, outgassing and volcanism last longer because they stay hot longer, right? So those planets could have longer-lived habitable climates than, say, planets that have both lower viscosities, right? So that could actually tie to planet composition. All right, already said that. All right, and the same thing, uncertainty in the seafloor weathering parameters, all right, also doesn't have a huge effect. So we tried different seafloor weathering activation energies, different kind of pre-exponential constants. The one thing that actually is interesting is if you change the dependence of the seafloor weathering rate on the amount of melt production, sorry. If it doesn't depend on melt production at all, right, that's this case. And if it depends on melt production rate more strongly, right, that's this case on the right here. And you actually get better climate buffering, right, and better, more planets can have long-lived habitable climates in this scenario than in this scenario. So actually that parameter ends up being pretty important for this. Right? Right, and so one last point and I'll wrap up. So I've talked all about planets with an Earth-like size, right? I haven't thought about planet size at all. All right, so what would happen is you increase planet size. All right, so we don't really know well, but I'll point out one study by a colleague of mine, Lena Nowak, which is very interesting, where she's looked at outgassing on stagnant lid planets as a function of planet size. Right? And what she found is actually, as you increase planet size, so this is looking at outgassed CO2 in bars. Here's planet mass and Earth masses. Right? So as you increase planet size, you get more CO2 outgassing, starting at 1 Earth mass and going up. Right? But then you see it drops off in really big planets. Right? Her calculations would show have almost no CO2 outgassing, right? And the reason for this, right, is that she's found that as a planet gets bigger, right, the pressures in the mantle are higher, and it turns out that most of the melting that she's calculating in these models occur at a depth where, or a pressure where the melt would be dense, heavy compared to the mantle, and it would sink down rather than going up to the surface, right? So, that depends a lot on mineral physics parameters that we don't know that well. So I would say we don't know for sure that this is what we'd find if we actually look at these planets, but it's possible that increasing planet size, right, could actually be bad after some limit, and big planets might be not outgassing CO2 to the atmosphere because the melt they produce is dense and sinks down. Okay, so I'll wrap up here with these conclusions. So start off, I showed that you've got habitable climates are possible on stagnant lid planets for a few billion years, something like 2 to 5 billion years, right? The kind of sweet spot for this is radiogenic heat budgets, right, that are as large or larger than Earth. So starting off with something like 75 to 100 terawatts of heat production and going up, right, is good. All right, planetary carbon budgets that are something like maybe 2 orders of magnitude smaller than Earth's to Earth's for this kind of conservative estimate. We actually found it was better, maybe something like 10 times larger than Earth's to 3 orders of magnitude smaller when we actually modeled climate and looked at seafloor weathering. I think an important implication of this is, so exoplanet radionuclide abundance is potentially constrainable from stellar observations, right? So we might actually be able to observe and predict, which planets, right, that we find might be capable of having long-lived habitable climates, even if they're in a stagnant lid regime. Right, so snowball states can be recovered from pretty easily, right, when ocean atmosphere exchange with the ice layer is possible, right? When it's not possible, it's much harder to recover, right? And only planets with really large stores of CO2 in their mantle could recover, right? And this would lead us to possible hysteresis effects, right, where stagnant lid planet evolution would be at low CO budgets determined by the initial state of the climate. If it starts in a snowball state, it might be stuck there, right? But if it starts in a temperate state, it might have a temperate climate for billions of years, right? So I'll end there and take questions.
Thank you, Brad. Time for questions. Here first, go ahead. Call whoever you like.
Yeah.
Yeah, so I'm not a geodynamicist, but I seem to remember hearing that people think that Venus has undergone these catastrophic resurfacing events. So if a more habitable stagnant lid planet didn't degas or produce fresh rock for weathering at a very steady rate, but had these more intense episodic events, how would that impact the climate, long-term climate?
Yeah, so then you'd be,
Repeat the question, please.
oh, so question is, would planets that have a episodic overturn like Venus is proposed to have, how would that affect their habitability? I think it would depend on how much CO2 you're outgassing at each of these overturns. You'd expect kind of a lot of outgassing from this volcanism versus how much fresh rock you've got around, right? So if you overwhelm that, maybe you get pushed into a state that's too hot, right? And the planet might get too hot. And also it would depend on maybe how long you have to wait for the next overturn. So at that point, you'd expect, probably weathering would be continuing, but there's not much outgassing, right? So you might have kind of spikes around when this overturn happens where the climate's habitable and spikes where it's not. I know Adrian Lenardic and Mark Jelinek have looked at some of this in papers, and I'm not sure if they've included the supply limited weathering stuff like I've done, but they argued that episodic overturn, episodic subduction events don't have a drastically huge impact on climate, so it might still be habitable even in that state. Yep.
Thanks for that talk. Do you have any conception of how young a planet would be to have a factor of 2 or 4 larger radiation heat than yours?
Yeah, so,
Repeat the question again.
oh yeah, so how young would a planet have to be to have these higher radiogenic heating budgets? So I was looking at all of this in terms of the initial heat producing budget of the planet, so normalizing all of them back to time 0, in order to get 2 times as much. So I based the range I looked at from work by a colleague, Cayman Unterborn, who's looked at trying to estimate heat producing element budgets for planets by looking at stars, and the range that he found by trying to focus on stars that have similar composition to the sun but just vary in these heat producing elements is basically the range I showed up to like 2.5 times Earth's heat budget. So I think there could definitely be planets that have heat producing budgets like that. And I didn't explicitly show age, but if you knew a planet's age and could estimate its heat budget from the star, I could kind of tell you where on these diagrams in evolution it could lie. Yeah.
So planets that have more carbon in them presumably have more water in them too.
Mm-hmm.
They kind of go together.
Yeah.
Planets form. And so what role does that have? If you got 10 times as much water?
Yeah, it would. Oh yeah, keep forgetting. All right, so what role, if planets have much more water, right, scaling up with their CO2, what role would the water play? So it would depend. I kind of assume that we've got seafloor weathering as a dominant process, so we've already got basically, water world type planets. if the ocean layer gets really, really thick, there's weird stuff that could happen, like ice is forming, and then kind of all this is out the window because we don't have the weathering reactions happening that I'm including. And then that could also affect the snowball recovery. If there isn't any land, you're always assuming that we've got volcanoes, or at least sticking up high enough to be above the oceans in an ice layer. But if there's a ton of water covering those up, then it's harder to get stuff to the atmosphere. So you really need to rely on atmosphere-ocean exchange in that case. Yeah, David.
So you've given a theoretical kind of overview of these stagnant lid habitability, but so one question I had was, I mean, presumably Earth plots on your plots because it's got the
Yeah.
right carbon amount,
Yeah.
it's got the right, but it's not a stagnant lid, it's
Right.
tectonic. So it seems to me that, you know, when it comes to actually testing this hypothesis with exoplanets, there's a kind of fundamental issue, which is how on earth do you tell a stagnant lid versus tectonic planet at a distance? And you had your two axes. You said you could maybe get the nucleotides,
Yeah.
which is the thing you had on the y-axis from stellar photosphere, and maybe get the carbon amount or some crude
Yeah, that would be
value,
hard.
but ultimately, because there's this degeneracy, isn't there? Because it could be tectonic, it could be stagnant. That's the thing you really need to know.
Yeah, so the question is, can we tell the difference between a stagnant lid and plate tectonic planet from observations and from at a distance, and how would that affect the results here? Yeah, I mean, I'm not sure how well you could. I would say kind of the point I'm making is if a planet in a stagnant lid regime at, you know, one of these sets of parameters can have a climate that lasts, a potentially habitable climate that lasts 3 billion years, a plate tectonic planet should have a habitable climate that lasts longer, because volcanism should last longer on a plate tectonic planet than a stagnant lid planet. So I would say that the estimates I give are sort of like the lower bound, and if it's got plate tectonics, that should be even better. So if we're looking for, planets to look at, you could say, the estimates from the stagnant lid regime are probably the worst case scenario for whether it's still habitable, and if it's got plate tectonics, that's probably better. So I would use this as a guide to say, planets that plot in our sweet spot, have kind of the best chance for maybe still having habitable climates today when we look at them. And yeah, I'm not sure we can tell whether they have a stagnant lid or plate tectonics, but if they do have plate tectonics, if anything, my estimates would be undershooting how long their habitable climates could last. So I was kind of going more for that angle than whether we can tell. You could presumably try modeling stagnant lid and plate tectonic end members and see, for this particular planet, at this particular set of conditions, how long would you expect outgassing to last with plate tectonics versus with stagnant lid, and then maybe use the observations to see which is more likely. But there'll be model uncertainties in that, and it's possible we wouldn't be able to tell.
One more.
Sorry, is tidal-genic heat budget negligible, or does that also play into this?
Yeah, so tidal heating, how that would play in. So I assume no tidal heating in all of these. So I would say if you have tidal heating and you have a orbital architecture that keeps that tidal heating up for a long time, that'll make things better. That'll make the planet stay hot longer, outgassing longer, and you'd get longer-lived habitability even than I predict here.
All right, well, let's thank Brad again for a great talk. For those of you who are here, we will be taking Brad out to dinner at about 6 o'clock today, so if you'd like to join us, either send me an email or come by my office at 6 o'clock over at PAB. And anyway, thanks a lot, everybody.